Hi, this is Brian Pinto, and you are watching a video for one of the ways of proving that the Collatz conjecture is true. I have discussed this method in a book that I am publishing. The book is titled My Two Cents, Part 1. Now, from the existing research, we see that there are a lot of aspects about this algorithm that are quite interesting. A search for the proof is interesting, yes, but the analysis of this problem reveals intriguing aspects of our number system. In this book, I have presented some of them that I found interesting. The book brings out an opinion that the sequence reaching 1 may actually not be a convergence to 1, and it treats the sequence generator as a state machine, that is an abstract machine. Then it discusses various aspects of the problem, including how to approach a proof in a simple way. Now, in this video, I would like to demonstrate only how we can prove to ourselves that this conjecture is true for all starting numbers 1 through infinity. To begin with, we will look at the Collatz function. We know when the number is even, we have to divide it by 2. And when the number is odd, we have to multiply it by 3 and add 1 to it. The result, we feed it back into the function again, and so a sequence is generated. Now, the sequence generated by the Collatz function varies from number to number. For some numbers, it's like short, and for some numbers, it goes really long. There is no way you can find a correlation visually. But there's one very interesting fact that we all know. It's a fact that whenever a number reaches an even number, it goes all the way down to an odd number. Every even number goes all the way down to an odd number. That means all these numbers, all the values that are even are related to an odd number. We can then build a table of all odd numbers and even numbers based on the relationship that we have. All we have to do is list all the odd numbers in the header, and for each column you take the odd number, keep on multiplying it by 2, and you build this table. This table in the book is called the cliff table. This table is also very important in approaching the proof. So what we have from the cliff table is a relationship between even numbers and an odd number. So every even number is related to a particular odd number, and we can analyze this by looking at the binary form of the even numbers and the odd number. You can see all the even numbers over here that are shown over here are left shifted versions of an odd number. Then what we do is we look at the operations in a total different perspective. Now, let us say, for instance, we have the number 6656 and we want to find the rest of the sequence. We would have taken the number 6656 and divided it by 2 repeatedly to get its odd pattern, right? The odd number, which is an equivalent in pattern, right? Then we would have multiplied it by 3 and added 1 to it to get the number 40, and then we would have gone again dividing by 2 until we get the pattern of 5 in the number 5, which is an equivalent of the number 40, downshifted equivalent of the number 40. But you can see that the pattern remains same all the way through, right? So we look at this in a different perspective and develop a different operation. What we do is we take the number multiplied by 3, and instead of adding 1, because we are not divided by 2, right? We take the equivalent of the number 1 for that level. the left shifted version of number 13 is 6656, right? So we have the level and we add that level to the number that you have multiplied by 3 to obtain the next pattern. This is the number 5, the same number 5 and equivalent to the number 40. So what we then have is this equation right here. We have our n multiplied by 3, and instead of adding number 1, what we do is we add the pattern shifted equivalent of the number 1 for that level. This is known as the ledge level in the book, and it is also known as the ledge power. It's one and the same thing. This x is the number of left shifts that we do and is known as the ledge exponent or the ledge index. So what we have here is a single expression, a single operation, instead of having two operations where we decide whether we have to do what we have to do with an odd number, what we have to do with an even number. We have just one single operation, and we develop a sequence generator based on this. So then what we have from that function is a sequence generator that looks like this. We can see the patterns advancing, as we move through the process. This one right here, from the most significant bit to the lowest bit, that is a 1, is called a floating binary form. And the floating binary form is equivalent to an odd number. And we have over here, as an instance, a sequence of odd numbers, or the orbit of odd numbers, that has a starting point 235. So the floating binary form has a leading edge and a trailing edge. The leading edge can do only 2 bits or 1 bit of advancement per iteration, but that is not true for the trailing edge. The trailing edge can do more than 1 or 2 bits. Sometimes it appears to slow down, but eventually the trailing edge catches up with the leading edge, and you get the pattern of 1 over here, which is equivalent to the odd number 1. At this point, we consider the Collatz sequence has reached the value of 1. So all we need to prove is that the trailing edge is faster than the leading edge to make sure that the conjecture is true for all starting points from 1 through infinity. But this alone can't be used for a proof. We need to ensure that all kinds of patterns are possible. The trailing edge can eat up all kinds of patterns and advance and reach the leading edge. So this happens for every number that we see. You can always see the leading edge advancing at a particular rate and the trailing edge finally catching up with the leading edge. Now the aspect of the leading edge advancing at a particular rate is, even however long the binary form is, it doesn't matter. It will always be at that particular pace. But we have to make sure that the trailing edge can eat up all the kind of patterns thrown its way. For that, we look at one very important aspect of the Collatz system, that is known as the first Collatz group. The first Collatz group is all the numbers starting right from 1 till 254. That is all numbers that can be generated by the 8 bits except for 255. For 255, all are ones, that doesn't belong to the first Collatz group, but you can actually see the important aspect of the first Collatz group is the maximum value that it can reach. Every number in there, any number that goes the highest actually goes up till 9232 and not more. So that is the absolute maximum of that first Collatz group. And we know that every number over here in the chase, the trailing edge always catches up to the leading edge. That means it takes care of all 8-bit patterns that are available. This brings us to a particular point, where we can claim that the leading edge always advances at a particular rate, and all kinds of patterns can be eaten up by the trailing edge. So let us think you have a very, very long binary form, not so small, but really long binary form. The leading edge is always advancing at a fixed rate, 2 bits or 1 bit, 2 bits or 1 bit. But the trailing edge eats up the first Collatz, eventually eats up the first Collatz group, then it goes to the next Collatz group, then the next Collatz group, and in that way it can advance faster than the leading edge, and it eventually will catch up with the leading edge. So no matter how big the number, the trailing edge catches up with the leading edge, and eventually we get a 1 which is equivalent to the number 1, and therefore we see the Collatz conjecture is true, that all numbers, all starting points from 1 through infinity can reach the number 1. This is without using a convergence. We just use the what is called as symbol dynamics, or it is a pattern based approach. So there you go. That is the proof that the Collatz conjecture is true. So finally, in this video, we have seen that for all starting numbers 1 through infinity, the sequences finally end up in 1. But this is not a formal proof with equations and such where you finally write an equation, underline it, and say, therefore the Collatz conjecture is true. Now, some good mathematicians may be able to derive a formal proof from this method or any other method, but this is an informal proof. Nevertheless, through this method, I hope you have also seen that the Collatz conjecture is true. In fact, we can actually say the Collatz conjecture is not really a conjecture anymore. However, the most interesting part for me while working on this was not about the proof, but what I saw and what I experienced with the number system and how they are interconnected. It is absolutely beautiful. This book that I've written brings out many such aspects that I have not been able to present in this video. And I would encourage you, if you are having an interest in this field, I ask you to look this simple book up, which any enthusiast or student can read. I hope you enjoy it. Now, thank you for watching, and all the best to your endeavors in mathematics.